Right. So, okay, what binary search do you know about? All you might know this at least that given a sorted array 1 2 9 12 16, you can find any element in the array in log n time, right? Or specifically log base 2 time, right? Or these many amount of searches, comparisons, whatever, right? So why is it so? Because first of all, it's sorted, and fact that the function is what we call a monotonic function, right? It's always increasing in one direction, right? Or it's always the trend is going in one single direction. It's not parabolic or something, right? So what happens? You are trying to find 9 in this, right? So you take a L, you take a R, you find mid. Let's say you're not finding 9, you're finding 2, right? So you find the mid, you check the tendency of mid with what you are trying to find. So mid is 9 and you're trying to find 2. So basically you say that okay, it is somewhere here now. So you shrink your R, right? You shrink it anywhere near mid. Okay, there are a lot of variations where you make it equal to mid or you make it equal to mid minus 1. Okay, and then you do the same thing again. What is happening over here? Can you understand? What First of all you have to understand what is mid. Mid is basically half distance between both, right? And when you are not satisfied with what mid is telling you, you shrink it. Either R shrinks here or L shrinks here. Basically, your search space gets divided by half, right? And this happens recursively. Again, goes half in some other direction, right? Again, it goes half in some other direction. And this happens recursively until you find your condition, right? So basically, every time you're reducing your search space to half, to half, to half, right? And at one point, it might be just equal to one number in the worst case, right? Search space. And that one number is something that you're looking for, or you have to be satisfied with. Or you have to report that, okay, it's not possible. It's not here. Like if you're trying to search 8 here, you won't be finding it, right? The thing is, you'll be shrinking your search space here and there, right? So, what does this depict you in respect of time complexity? We have discussed this a lot of times, right? This is uh, log n, and this is something what I call binary logic, right? You keep dividing something by 2, you keep multiplying something by 2, and the time complexity turns out to be log n, right? So this is why the time complexity is log n, right? And this is the standard binary search that you know about, right? Uh, can someone tell me if you can understand if I say what is binary searching the answer? Okay, binary searching the answer. I should or something shrinking the size search space by half. Yeah. So can anyone tell me what does this mean? Exactly. Basically, it's searching the answer, right? But you do it in a binary fashion, right? So searching is lot more efficient now, right? Just like we did for binary search. Searching the answer within a known range, yes. But we are binary searching it, right? So you are always shrinking your search space by a factor of 2 every single time. So in the worst case, you'll just take log n time to find your answer, right? But does this imply for everything? Like for sorted array, finding an element in sorted array is fine. That you know about, right? Where else can it be applied to? It can actually apply to all the monotonic functions, right? Now, if you don't know about monotonic function, again as I told you, it just grows in one direction, right? It can even be a plateau at some place, but it will never go in other direction, right? So it's easier to search when it's always in the single direction. It's something close to sorted, right? And now how you can perform binary search on sorted elements is because you know where an element lies and you know where you have to go from there, right? If you're searching for this and you come across here and you know that it's more than this, so you push your L, right? Similarly, it goes with R. But now I'm going to tell you how to use it for any general problem, not just for searching an element, right? So actually, before understanding that, actually I want to discuss a case. I think it happened in some city. Okay, so what happened was there were a group of scientists, right, and their bike was stolen. Okay, this came in news actually, and it was pretty funny. So what happened was the bike was stolen and they filed an FIR, right? And the police asked for a camera recording of the location where the bike was. Okay, so they shared the camera recording, which was like 15 hours or something, 15 20 hours. Okay, and there was a very heated argument between those. Police were saying that I have no time to watch this complete recording for 20 hours, and the scientists were saying you can binary search it and it will take less than a minute to find it. Right now, if you can understand it, what they were trying to say is like you let's take the complete recording, right? 0 to let's say 20 hours, right? And you check whether at 10-hour mark if the bike is there, okay, if the motorbike is there in the recording, right? If the motorbike is there, it means that it has been stolen later, right? Not right now. So you again you bring your L here now and R here. Now you search for 15-hour mark. Now you check whether a motorbike is here in the recording. If it's not here, it was stolen earlier. So you can actually binary search it, right, in the whole recording. You don't even need that many time. You basically link what log 2 of whatever second you need, right? Let's say the lowest can be, let's say in 1 second it's stolen. It's not possible that they just need 1 second window to steal it. But let's just say it just take this much time to actually, or these many comparisons to actually find when the bike was stolen in a 20 hours video, right? So, what do you take from this? Like, I hope you understood this idea at least, right? How they were trying to binary search in the whole recording. You don't have to sit and watch it for 20 hours, right? You can just check if it's not here right now, you go back. If it's here, you go front, right? And you just need these many comparisons actually to search it over, right? And what is this? This is something, uh, sorry, someone speaking.
Yeah, how is it log 2? Like, is it n by 2? If I'm
No, no,
not
no,
wrong,
no,
like, we are just split.
no. Okay,
The
okay.
worst case can be n by 2, right?
See, can you understand that how I'm binary searching it? First, I'm searching in the
Yeah,
10th
yeah.
hour mark, right?
Yes.
Then, if the bike is, I'm going to 15th hour mark. You see that my
Huh.
space is reducing by half every single time. Half.
Yes, yes,
Next,
yes.
it goes
Okay.
half, right? It's just like binary searching, right? Exactly.
Kinda like, yeah,
Yeah, I'm shrinking my search space by half every single time, right?
yeah.
So,
Same logic applies for like the DCC that you have given before. Like
yes,
for time complexity. Yeah.
yes, exactly. And
Okay,
basically,
okay,
time
okay.
complexity
Got
is
it.
number of times you're doing the operation, right? So if here the
Mm-hmm.
operation was looking whether the bike exists at that particular moment,
Yeah, yeah, yeah. I
right?
got it. I got it.
So this is something close to 10 raised to the power 5, right? Which should be something close to like
Mm-hmm.
17, 18. So basically, you just need to check the recording 18 times to find when the bike was exactly stolen into 20 hours long video, right?
Mm-hmm.
So yeah, this was pretty funny. Like policemen were unable to understand how is that possible.
Yeah.
Cool. So like what I want to explain from this is that like how are you verifying where to go now, right? How are you verifying? So let's say one is bike is there, right? Bike exists. Zero is bike doesn't exist, right? Or let's take it the other way around. Okay, let's make it like zero is bike is not stolen and one is bike stolen, right? Now, if you try to look at the timeline and if you write 0 and 1 for every second, how do you think the 0 and 1s will look like? It will look like 0 0 0 0 0 0 0 0 at some point. And let's say the bike was stolen in 17th hour 35 minutes, right? So, up till 17 hour 35 minutes, you'll just have zeros, right? After that, you'll have 1 1 1 1 1 1 1 1 1. Why? Because bike is stolen. Even if you check at 19 hour mark, the bike is stolen. Even if you check at 18 hour mark, bike is stolen, right? There's no changing it. And can you see this is a monotonic function, right? You have 0 0 0 0 0, then you have 1 1 1 1 1 1 1 1 1. So if you binary search, where can you binary search the difference where this is changing? See, L R, right? See, I'll write the whole binary search here. So L is initially 0 and R is basically, let's take it in seconds. Let's say it is 10 raised to the power 5 seconds, right? So while L is less than equal to R, what I'll do is if uh, stolen at mid, Okay, and mid is always L plus R by 2. Okay, again, there are a lot of other ways to compute it, and I won't go into detail. And some people actually ask you to write mid like this due to some integer mm division, but we won't go in detail. Just use L plus R by 2 right now. Right. So if bike is stolen right now, what does it say? If it's stolen, it's 1, right? So basically you shrink your R space by mid minus 1, else you put L by mid plus 1, right? Right. It is this simple. Right. Now understand what will happen. Where will this end? Right. If you just see your L and R, this, let's say this is mid right now, right? And you see that the bike is not stolen, right? So if his bike is not stolen, you put your L here now, right? Your L proceeds here. Now you find your mid here, right? You check, is the bike stolen now, right? You'll get, yes, the bike is stolen. So you bring your R here, right? Actually it's minus 1, but let's just, for the sake of understanding, I'm putting it like this, right? Now you again take the mid, right? Let's say the mid is here. You check, is the bike stolen? It says no, so you bring your L here, right? Now say if the mid is this, you bring your R here, and you check, is the bike is stolen? You say yes, it's stolen, right? Now just understand that L is actually mid plus 1, right? So if this was mid over here, L is going to cross R, right? And L will come here, crossing R, right? Or it can be the other way around as well, right? But right now, actually this actually depends on what is happening when it's equal. Even okay, right now it's just binary function, so it's fine, right? There can be functions which compare greater than, less than, or equal to, right? So where the equal to lies actually tells you a lot of thing about the function, right? But just here you understand that what happens here when the mid comes to R, when L and R are this close, right? When L and R are this close, let's say the mid is here, right? But I know that due to integer division it will lie here, right? We'll do the exact thing, but understand that when mid comes at R, okay, and when you assign L to mid plus 1, it will cross here, and this will actually break the function, right? Right. Or actually, let's write it like, let's do it according to this exactly, right? So when L and R are, let's say, at the junction exactly, okay, 0 and 1, and I think they shouldn't be equal then here, right? So what happens? L is here, R is here, right? Your mid will come here, right? Give me 1 second, give me a second. Right. So mid will come here, right? And you'll say that okay, bike is not stolen. So what happens? L becomes mid plus 1. Basically L comes here as well, right? But the while condition said L should be less than R, right? And so you break out of this, right? And your L is where the intersection is happening. Can you understand this? Your L is where the intersection, or where the number is changing, right? So where your 0 1 intersection is happening is where you'll end up with L. And you can, in the recording, you can check this position. This is the position where a bike was stolen, or you go 1 minute earlier. Between this position is when the bike was stolen. Can you understand how I binary searched it? I kept decreasing the sample space by half, by half, by half, until I came to one single point, right? So if there the sample space was 10 raised to the power 6, I kept on decreasing it by half until I reached 1. So this just takes log base 2 of 10 raised to the power 6 steps, right? And I came to the exact point where it changed, right? So finding this exact point just took log n time. Anybody has any doubt in this, ask, because this is the basis of what I'll be explaining later. This is really very important to understand. Your whole binary search depends on this. right? So now basically you can binary search on any monotonic function, any problem that can produce a monotonic answer, right? Like like even when you search in array, the monotonic function that you use is, so fx is actually equal to the monotonic function is current element, let's call it current, greater than or less than whatever you use, it's monotonic. uh, yes, let's use greater. Is current element greater than target? This is the monotonic function you use when you search for an element, right? In a sorted array. So if your array was 1, 3, 5, 9, 12, 16, 32, and you are searching for, or let's say we are writing a lower bound function, okay? You might have heard of this. In C++, there's a direct library or direct function to use lower bound. So lower bound finds an element that is greater than equal to whatever element you are giving. Okay. So here let's try to find lower bound of 10. Okay, I am finding lower bound of 10, and my function is the current element greater than 10, right? You start here L, you start here R, you find, let's say mid was let's not take 10 actually. Again, I always take elements that towards the center. Let's take 17, right? You start here, now you check whether mid, okay, now tell me how will this function look like over all these elements. It will look like, is 1 greater than target? No. Is 3 greater than target? No. 5 greater than target? No, 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 yes. And what do you have to find? This element, right? Greater than equal to 17. Now this pattern is very familiar, right? 0 0 0 0 0 0 1, and you have to find this. Can you understand that you can find it using binary search now? The whole purpose of binary search is to find the 0 1 intersection. That's all. You have summarized the binary search in just one statement. You have to find the 0 1 intersection, right? And how you construct your 0 1 intersection is by finding a monotonic function to that problem, right? Monotonic function is that will always, that won't change the path, okay? Like it will just go in one single direction, right? Again, like binary search is a very obscure thing, okay? You have to solve a lot of problems, so you have to understand it by looking at the questions to how to properly use it, okay? So lower bound is one such thing, right? And apart from that, this 0 1 thing, please remember it, right? Now I'm going to talk about something, okay? I'm going to give you an example of this again, okay, so that you understand it better. So it's called minimization and maximization. Maximization. Now I'll tell you something and you have to remember that all minimization and maximization problems, just mug it up, can be solved using binary search. Using binary search. Now tell me why. Somebody explain this to me with respect to the monotonic function that I talked about. Anything that you can understand from this statement. What are minimization and maximization problems? That I'll tell you first. So it's like, given a problem, you're like, minimize the number of steps, minimize the cost, maximize the number of elements, maximize the profit that you can obtain, something like that. Okay, so those are minimization maximization problems. Now, can you
effect in any better way. It's
Usually,
not a
these sort of
competition.
problems require some sort of combination of elements that are chosen greedily. So to find those elements from the given
That's what I'm insisting.
list of
Don't
elements we
create
have, we
toxicity
can
any further.
apply
Okay?
binary search.
Please
Maybe
maintain a good.
that's what we have.
Yeah,
to do.
healthy is okay.
Okay, I'll actually explain it to you. I think it's a bit hard to directly come to that idea. So basically, what I want to say is, say the question says, find the minimum amount required to do whatever. I don't care. I don't care about the problem. I just want that the question asks you find the minimum amount x that is required to do something. Now tell me something. If x amount can be used to done that particular thing, or rupees x is sufficient to do that thing, tell me, isn't rupees x plus 1 also sufficient? Right? If say you are going to the shop to buy something and that thing costs 10 rupees, so even if you have 15 rupees, 20 rupees, 25 rupees, is that a problem? No, right? You can still buy the same thing, right? But having 9 rupees, 8 rupees, 2 rupees, 1 rupees is a problem, right? So again, everything come back, and can you see that this again forms some kind of monotonic function? How? You ask, right? Your function is x sufficient to do whatever is required? Okay, to do whatever work. You ask this, right? And tell me what happens. For x, it will say yes, it's sufficient. For x plus 1, it will say yes, it is sufficient. For x plus 2, it will say yes, it is sufficient. For x minus 1, it will say no, it's not sufficient. X minus 2, it will say no, it's not sufficient. And this goes on. And this goes on in front as well, right? Now can you understand that the first place where x becomes sufficient is the minimum cost that you have to find, and basically the answer to your problem. So you can again binary search this 0 1 junction, right? And this x is actually your minimum cost, right? Understand how this is a monotonic function. Understand how monotonic functions can be used, like how binary search can be used to find an answer to monotonic functions, right? I'll give you an example. Okay, I'll give you an example if this is you're not able to understand like how the monotonic function is being created. Let's take a problem. Right. Again, see, some people might know it already. Okay, and for some people it is entirely new. So for people whom it is entirely new, it will be a bit hard to understand. Okay. Now this problem is very popular, and a lot of you might have seen it already. It's called aggressive cows. Right. It's very popular. Right. So farmer John has built a long barn. Okay, the stalls are located on a straight line. His cows do not like the barn layout and become aggressive towards each other once put into the stall. To prevent the cow from hurting each other, farmer John wants to assign the cows to stalls such that the minimum distance between any of two of them is as large as possible. What is the largest minimum distance? Okay, I'll paste it. So basically you are given number of points, right, and the number of cows that you have, right, and if you would assign those cows in some of those places, right, so you are given, you have three cows, and you have coordinates as 1 2 8 4 sorry, this is very hard to see here. 1 2 8 4 9, and those are supposed to be integers of stall locations x1. 1 2 8 4 9, so they're just sorted so that they are linearly arranged. 1 2 4 8 9. Okay, so you have to put 3 cows such that you want to minimize the distance between them. Okay, so you have to put 3 cows such that the distance between them is you have to maximize the distance between them. So you have to put them what is the largest minimum distance. So basically you have to find, so wherever you put them, let's say if you put them one here and one here, then you have to find the distance between them. This is 3, this is 4, and you have to report the minimum distance 3. So you have to find the largest minimum distance. Okay, so tell me, how does the monotonic function for this looks like? Now I'll tell you, tell me if you understand this. So f of some distance says that is it possible that distance between every cow is at least x. Is it possible that the distance between every cow is at least x? This is the monotonic function that you are trying to create, or at least d, I'm sorry. Right, so this is the monotonic function. Now tell me, how is this monotonic? Now if distance between every cow, if it is possible to put them in this such that distance between every cow is 3, right, let's just say it is possible to put them in the in this barn. They are barns, right? Yes. Or they are stalls. If it is possible to put them in this series of stalls such that minimum distance between them is distance between them is at least 3, right? Or then now understand what is at least 3. At least 3 can be at least 1 as well, right? So if it is possible to put them in barns as the distance between everything is at least 3, it is also possible to put them in the stalls as the distance between them is at least 2. Let's understand it. Let's say cow 1 is here, cow 2 is here, cow 3 is here, cow 4 is here. The distance between it is like 3, 4 and 8. Let's just say it's something like this. Okay. This might not be the most optimal answer. I've not even revealed you what x coordinates are. Let's just understand what I'm trying to say. So tell me, if you ask them for this configuration, hey, is this possible such that the distance between every cow is at least d, right? So for what d's you will get yes. For 1 you will get yes, for 2 you will get yes, for 3 you will get yes, right? Because you're asking, hey, is the distance between every cow at least 1? You'll say, yeah, it's at least 1. It's 3, 4, 8. You'll ask if distance between every cow is at least 2, you'll say yes. Distance between every cow is at least 2, you'll say yes. But after 4, you'll say no, because this is 3, right? Right. So instead of finding what is the minimum distance, or instead of finding what is the minimum distance you have to put the cows in this stall, let's say x1, x2, x3 up till x of n, how about asking, is distance minimum distance, or like is at least distance d possible? Right, can you understand that this becomes a monotonic function? Right, so to find the maximum distance, you start with whatever maximum minimum can be. So maximum distance can be distance between x1 and xn, right? If you're just putting 2 cows, right? So let's just say the distance is like 10 raised to the power 6, and the smallest distance that you can put is, let's say 1, right? You cannot put 2 of them in the same same stall, and of course the distance in 2 will at least be 1, right? Now you take the mid, right? You take the mid of these and you ask, is at least mid distance possible? Now right now just forget how we are computing this. Okay, now to compute this you can take O of n time, right? To compute this you can take O of n time, right? And the number of times you will be computing will just be log n, right? Because again it comes back to binary search, where you are just doing log n comparisons, log n operations, right? Because every time your search space reduces by half, right? So log n times you'll ask, hey, is at least d distance possible? Sometimes you'll get a yes, so you'll pull your L, right? So if it's possible, it might be possible to make it even greater, right? So if you'll say, okay, if 2 distance is possible, maybe it's possible that 5 is also possible at least. So we'll try to shrink it here. When it says that okay 10 is not possible, so you'll say okay 10 is definitely not possible, you'll try to search something less, so you'll shrink your R. So by doing this, every time you're reducing a search space by 2, so after log n times you'll actually come to that junction where it's possible at one point and just the next point it's not possible. So that junction, right, that junction will be the maximum of the minimums, right here. Let's say at 8 it was possible and at 9 it was not possible, right? So at 8 it will say okay it's possible, 9 it's not possible, so here you will break out of the binary search, right, and you'll report 8 as the answer. So from the question being what is the minimum distance, you just change it to is the distance possible, and you just binary searched over it, because you know that this is going to a monotonic function, because everywhere you see an at least, it's a monotonic, because at least itself is monotonic, right? If you are searching for at least 5, that is also 4 3 2 1, right? So even 1 is at least 5, 2 is sorry, it's the other way around. Like even 6 is at least 5, right? Even 7 is at least 5, even 8 is at least 5, right? So at least is always a monotonic function in such sense, right? Again, if this is you mean threshold by means of at least? Yes, any threshold, yes. So like let's like try to compute this function. Fx is at least x. Try to let's call x as 10. Try to compute this function on a number line. Okay, if it's at least x, you give a 1. If it's not, you give a 0. Right, and you'll understand that for everything between 1 to 9 it will be 0, and after 10 and everything after that it will become 1. So this is a monotonic function, right? You can always binary search over it. You can always binary search over at least this, right? I'll discuss one more example. This is, I think, a particularly hard example, right? So I think this was yesterday or day before yesterday's problem of the day for lead code. It's called task scheduler. Now, can you find the pattern? The question says return the minimum number of intervals. It is a minimization problem. Again, I'll put it here. I'll just quickly explain it. So you're given an array of CPU tasks which is represented by letters A to Z. So something like A, B, A, D, K, Z, A, B. Each of the interval allows the completion of one task. Task can be completed in any order, but there is a constraint. Identical tasks may be separated by at least n intervals due to the cooling time. Return the minimum amount of intervals required to complete all the tasks. And a cooling. So n is cooling time. Okay. So basically what it says that if n is 3, after you have executed a task of A, so there should be at least 3 gap, then only you can execute a task of A. Okay, and if say A, B, A, right? So let's say the only tasks were A, B, A and n was 3, so it will look something like A, B, idle, idle, A. Right, yes. So basically you'll take 1, 2, 3, 4, 5 cycles to do it. Right, now tell me, for this particular example, if you can take 5 cycles to complete it, can you take 6 cycles as well to complete it? Yes, right? Can you take 7 cycles, 8 cycles, 9 cycles to complete it? Yes, right? If 5 is possible, even 6 is possible, right? What do you have to do? You remove this, put an idle here, Put a here, make it 6. Yes, this is not optimal, but this is possible, right? What I'm saying is it's possible. So let's say 5 was the most optimal answer. Then for 6, 7, 8, 9, whatever, it is also possible, right? So at 5 it's possible, 6 it's possible, 7 it's possible, 8 is possible, 9 is possible, and from 0, 1, 2, 3, 4, okay, let's say 0 doesn't exist because you have at least one task. So it's not possible, not possible, not possible, not possible. Again, there is a monotonic function here. Right. Now what is the function? F of x says, can all the tasks be done in x cycles? Can all the tasks be done in x cycles? Let's forget how you calculate this function. Don't bother understanding how you calculate this function right now, but tell me, if you have a function like this that works in O of n time, okay, again it should work in linear time, always remember. If you have a function like this that works in linear time, so when you put this function over binary search, so you binary search x, right? So how many times will you be computing this thing, that can all the tasks be done in x cycles? You will be computing this only log n times, right? Because you're shrinking your search space by 2 every single time. So this will take n log n complexity, and this is called binary searching the answer. You find a monotonic function. I think in this problem it will be optimal to finish all the processes in decreasing order of their frequencies. Okay. Yes. But again, like okay, a greedy solution exists. Okay, there are some binary search.
Get a greedy, I get a formula like we have to get the maximum frequency and number of maximums,
Yes.
and the length of the array plus 1 into the maximum frequency minus 1 plus number of max. It gives a little bit pattern, but in some cases it is not working.
Yes.
In that case, we have to take the length of the array. It's my greedy intuition.
Yes. No.
It is working.
For
I
like
don't know.
cases like this, and if you
Hmm.
have like a gap 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 a gap 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 a, it's possible that everything
Yeah.
might not fit. It might be something like b
But
b,
yeah.
c d e f, then g h, right? So
Hmm.
what I'm saying is, forget how you are calculating it greedily for now.
Yeah. That's what.
Yes,
It's
simplify
too
things.
new to me. It's the problem.
Yeah, this I understand. So like just try to form a monotonic function out of this, and also the only thing that you have to understand is how a monotonicity is existing here, right?
Okay.
Yeah, because see, you have to minimize it, right? Anyway, so you just have to compute this, and over this you can binary search it.
Hmm. So we get a monotonic function. Okay.
Yep. So wait, I'll actually explain it to you how to use the monotonic function. So again, you come L becomes 1. Let's say minimum 1 is required, right? R becomes, what do we take as maximum number of cycles, right? Let's take that maximum number of cycles can be 10 raised to the power 18. It doesn't matter. Okay, or maybe whatever upper bound to come up with. It doesn't matter.
So we can be it can be like n to the number of elements or tasks that has been given, right?
Yes.
Because if each task is the same task.
Yes. Yes. So it can be n into number of tasks. So basically, yeah, okay. Let's call it number of. Let's call it nk. K be the number of tasks. Right. So again, you do the same thing. You write a binary search, while L is less than equal to R. Right. Now, where you write this condition, right? Where your monotonic function goes. Where f of d, if f of d, so if it is possible to do with this many cycles, it might be possible to do with less number of cycles as well. So you reduce your right element. Okay, and d is L plus R by 2. So if it is possible to do with these many elements, it might be possible to do with lesser number of cycles as well. Otherwise, if it's not possible to do with given d cycles, it might not be possible to do with less number of cycles as well, right? So you have to move forward. So L becomes mid plus 1. Okay, and then you can write this function separately. What this f of d will do? Basically, it returns a boolean. Okay, it returns a boolean, and f of d you can write. Okay, and what this function should answer, whether it is possible to do it in d cycles. Yeah, Aditya.
So, but how will we get the intersection from this key? Okay, every time I'm looking into it, I have to check the adjacent one as well, right? Adjacent f of d as well to make sure that I did not go over the intersection. Oh, never mind. I understand now.
You will always
Second
go over the
iteration.
intersection.
Yeah, second iteration. If you go over, you know, okay, this is the mid. You get the midpoint there.
Yes.
Understood.
And actually, this will only exit when you go over it. It is always
Right,
true. It
right.
will always going to happen. So every time you have something like this, again, binary search is something that you have to implement on your own and try it. Okay, I had a lot of problem solving binary search problems initially. Okay, but you try to implement it. See how the pointers are moving. See how the mid is moving. Okay, then try it. Okay, maybe try this problem. Give yourself an array and try to find the position of this using binary search. Okay, do it yourself. Make your own test cases, try to solve it, see if you're finding it every time using binary search. If you're able to find it, if you're able to do it, then just understand that this is just a monotonic function that you can create out of any given problem,
Understood.
right?
Anytime, my intuition right now is anytime the value switches from being what it was to the opposite side, that means you found the correct answer, right?
Sorry.
The moment the value switches, let's say if I was getting zeros, and the moment I get a one, that is when I have found my correct
That is how
value.
you search linearly, because 0 0 0 0 0 oh 1 first one. But with binary search it's not same, because sometimes your mid is here, other time your mid is here, then again your mid
Right.
might come here, so you'll go over 0 1 0 1. That doesn't matter. What matters is, say LR is here, then R shrinks, then L shrinks, then R shrinks, then R shrinks again, then next time L shrinks, it goes over R. So that will tell you that this is a 0 1 intersection,
Understood.
right? So basically, again, try to write your own binary search, right, and fix one single template. This is the exact template that works for me, and the answer is always L minus 1 in this, every single time, because R usually happens to be here and L jumps over it. So L minus 1 becomes this, usually. Something similar. But again, the thing is that once you write it, once you see that your particular binary search works for you, right, then keep using the same thing. Okay, don't change it. There are a lot of things, like either you putting an equal to here, is it minus 1, plus 1, or just mid? Okay, and what your final answer is. That depends on how you write binary search, right? People have different kind of binary search. You can use what I'm using right now exactly. This works always. Okay, but and like
Bhaiya, could you explain the f of d part? Like, what does the f of d function do?
okay. So f of d function is just a validation for your d, and what your validation for d is what the question is asking, right? So the question is asking you have to complete in minimum number of cycles, but your f of d says whether whether it is possible whether it is possible to complete in d cycles. This is what my f of d says. Right. No.
Yes, Bhaiya. And Bhaiya, in the R part, n is basically the number of processes, right?
Yes. No. N is the k is the number of processes. N is the minimum distance that you have to keep in between.
Okay.
This you don't have to care about what this is. You can just take some very large values. That doesn't matter, because anyway, for a very large value, it will again be like, yes, it's possible. Like again, go to the same example. When you're going to a shop, you have to buy something for 5 rupees. Even if you have like 5 million rupees, you can still buy it, right? So that again, it doesn't matter what is the right limit, right?
Yes, Bhaiya. Yeah.
Right. I think it will be better if I'll solve a problem exactly then, right? So again, I know this is new for a lot of people. because this idea itself is very new. But this idea will help you to solve so many kind of problems. There are so many problems that might just require greedy, but you have to think a lot. Like what is exactly maths you have to apply, or what exactly is happening there. But if you just throw it to binary search, ask the binary search, is this possible? And binary search over this, right? Binary search over the value, you will always get the minimized or maximized value. Okay. Now, okay, let's just see this problem, and I think it might be a bit easier to understand using this problem. Right. So, uh, see, right, yes. Actually, don't bother reading it. I'll explain it to you right now. Just give me 2 seconds. The number of moons and the amount of damage that needs to be dealt. Okay. So, leave reading. I'll just explain it to you. Relax. So the question says you are given n moments, okay, to enter the number of monocarps attacks. So, and here 5 is the second when the ith attack is performed. So you are given n attacks that are performed, right, and the health of the monster, okay, and you are given at what particular second you have attacked it, right? Let's say you attacked the monster 4 times, right, and each attack monster's health is 100, and the attack was at first second, 25th second, 40th second, and 100th second, right? Now what you have is you have a dagger that's poisonous, okay. Now the dagger's damage is none, but the thing is every time you hit it to the monster, it does damage for few amount of second. Let's say for x second it will damage the monster. Every second it will damage it by a point of 1. So let's say it damages the monster for 10 seconds, right? So what happens is if you hit the monster at the first second, at the 10th second the monster health will be 90, right? Now let me just confirm it's at every single second starting from the first. So in the first example, k is equals to 3. Damage result is 1, 2, 3. Yes. So if you attack the monster with x equals to 10 and you are attacking at all the intervals, okay, you don't have to pick at what interval you're attacking. So let's say x was not 10. Let's say someone is trying to say something.
Yeah, what if let's say x is some value, let's say 10.
Yeah.
I attack the monster at 1. I also attack the monster at 5.
Yes.
So what happens then?
Lapses. The original lapses. You don't stack it.
Okay.
That was what I was trying to say.
But the
So
duration will just increase then,
yes.
right?
So here if x was say 10 and you have seconds like 2 and 3, so you will damage at first second, you'll damage at second second. Now you'll damage from 3, right, to let's say 5, right? So you can see that you are damaging at 3 anyway, right? So it becomes 3, 4, 5, 6, 7. So it becomes 5 here, right? This resets, the poison resets, right? So 1 and 3 is where you attacked, right? Now the question says what is the minimum x required to kill the monster? Okay, again this is a minimization problem, right? How, I'll tell you right now.
So what I'm getting, the first intuition that I get for all of these problems, that is the aggressive cow one and this one, is why can't we solve them by simple division? Like in this one, let's say if monster's health is 100 and x is 5, so I know that okay, I need to make 20, because anything lower than 20 I know I can't get that 100 value. Anything higher than 20 I'm like, okay, this is
Lower than 20 or 25, because they have 4 points, right?
oh right, sorry, 25 then. Yeah, if monster's health is 100 and damage is for 4 seconds, so 25 times, right?
So you have to check everything from 25 to 26 to 27 to everything, right?
But then what I'm trying to say is, if they're asking for the minimal value, right,
Yeah.
we can just divide 100 by 4, and that way we get 25, right?
No, but
Why can't
25 might not be the answer, right? If the stuff was 1, 2, 3, 4, 400, you know that 25 is not the answer here. Because if you take 25, you'll be just doing 1 damage here, 2 damage here, 3 damage here, then 25 damage from here. That's just 31 damage.
Understood.
Right. No, again, what I'm trying to say is a greedy solution might exist for some problem. I'm not denying that. Okay, but again, there will be some problems where a greedy won't exist. Right. There will be some problems where to calculate that whether putting x is equals to some value viable, you need at least O of n time. And you need to search it for every number there, is what I'm saying. So if you try this brute force, you have to search it for 25, for 26, for 27, or let's say you don't know the 25 limit, you start from 1 and you search it all the way up till the first place where you can say that, okay, this is the minimum damage that is required.
Understood.
Right. But again, if you see that becomes a monotonic function, 1 will be 0, 2, 0, 3, 0, some 0. At
Right.
some point, it
Right.
becomes 1, 1, 1, 1, right?
So it's applying linear search on monotonic function.
Yes,
Okay.
yes. What we were trying was linear search. Right. Now, again, how is this monotonic? Understand. If a damage of x can kill the monster, if the dagger damage is x, it can kill the monster. A dagger damage of x plus 1 can also kill the monster. X plus 2 can also kill the monster. Right. So again, this becomes a monotonic function. So you just have to find whether, okay, so your whole question reduces to you first make a monotonic function which says, is x damage sufficient to kill the monster? Right. This is your monotonic function. Right. And how you solve it is, you take the minimum damage as 1, right? 0 cannot be taken, you have to do some damage at least, right? You take the maximum damage as whatever the maximum health constraint is given in the question. So it says the maximum health can be 10 raised to the power 18. So it's possible that you have to do equal amount of damage. Okay. Then you start your binary search, same thing, while stuff, calculate mid, right? Now again, what do you do? If f of x, if it is possible to kill the monster at x damage, it might be possible to kill the monster at some lower damage as well, right? Remember the x plus 1, x plus 2, x plus 3 part I explained. Otherwise, if it's not possible to kill it at this much damage, it's not possible to kill it lower damage as well. So you increase left boundary, and your answer is always L minus 1. Right. Now, this was what I didn't discuss up till now. Let's calculate fx, okay, for this problem. Okay, so same example, 400 and 125, 40, 100. Right. Now you are just given x. I'm making the function f of x. Okay, boolean of f of x. Okay, and let's say I have this array with me. I have this damage with me. You can just pass everything as a parameter. Right. Now it should return a boolean, right? So let's take damage. Okay, I'm just telling you how to solve it. This is greedy. Okay, this is greedy, or this is just maths, but I'm still explaining to you so that you explain the whole idea first. So damage is 0, right? Now from 1 you add x and see if you are reaching 24, right? If you are not reaching 24, you are doing complete x damage at here, at this one, right? So 124, 40, 100. Okay, I'm not going to write the code, I'll explain it to you how this works. So if you add x and you are not reaching 24, you can do x damage here, right? Or if you are reaching 24, you will just do whatever damage from here to 23, right? Basically you are doing 24 minus 1 damage and here, if x is greater than the difference. Again, add x here, see if you are reaching 40. If you are reaching 40, see, the thing is that if you are reaching 40 or if you are reaching more than 40, this the damage will be reset at 40. So you'll just be doing damage until 40 minus 24. You'll just be doing this much damage here. right? Now you add x here. Let's say x was less than this, so you'll do x damage here. And in the last index, you'll always do x damage because there is no upper bound here. It will never lapse, right? So this is the total amount of damage you are doing, and then you return whether damage is greater than equal to h or not. You just return this. So if it's greater than equal to h, then it's possible to kill. It's not possible to kill. So you return this boolean function here, and then it binary searches over this, right? So again, binary search takes log n time, and this function is taking O of n time, right? So O of n into log n for a binary search solution will always work. Even for a greedy solution where you just require O of n time, O of n log n will always pass. Okay, so a binary search solution will always pass for a greedy solution if you can find the monotonic property of it, right? Tell me if you understood this or not. If you're starting right now, okay, if you are seeing this for the first time, it might be hard to understand. So I'll in the last slide I'll actually tell you what all to do first, then try attempting problems. Right.
How
One
do
that I
you
had
think
was
that the current
this,
four games,
the output
current
or
four
the
contents are going
amount
on
of
with?
calculations that we'll do to reach the
Hmm.
target value
No,
Hmm.
no,
is
I was
heavily
asking
dependent
them.
on
Yeah,
starting values, right, for LNR. So is there any way to optimize those values to make sure, okay, I'm ruling out some extra calculations or extra,
Do you need to
like,
do that? You are trying to
uh,
reduce the search space even at the start,
right,
right?
right,
I don't think that is required.
okay,
See,
cool, cool.
in the worst case, like even in the best case, let's say you reduce the search space by 2. Like from 1 you brought it something to 25, right?
Hmm.
But again, the right limit was 10 raised to the power 18, right?
Right, understood.
Right,
So it's
so
not
it
matter that
basically
much.
made very less difference. Even if you are able to bring it to something like 10 raised to the power 9, or let's say very high number, let's say what, 2 into 5 into 10 raised to the power 17, a number that's that high, right? So can you understand the difference between this and this is 5 into 10 raised to the power 17, and distance between where
Right.
we are trying to start is also the
Yeah.
same thing. So basically it's just one operation that costs us that.
Exactly. Right. It's
So
not going to affect a lot. I understand.
yes,
Yeah, yeah.
yes, yes. So like this is like the binary logic. Even if you are reducing something so much, when you increase or decrease by a factor of 2, it is immense. Okay, so it doesn't matter. Sorry. Right. Actually, there were few more problems that I wanted to discuss, but again, I see that a lot of you are not able to understand it properly. Right. Uh, let's see if there's something else that we can discuss. Okay, for this particular topic, please ask me a lot of queries. Okay, I want to see the threads flooded. Okay, because the questions aren't very easy. Okay, because I wanted to learn the whole idea of binary search. Now, I'll just recap everything. Okay, I won't discuss harder problems now. Okay, I'll just recap. So, how to learn? Okay, again, binary search is something that you have to implement yourself. Okay, please try to implement it. Try to understand how the pointers move, how L crosses Y. Okay, so first implement binary search over this 000. You can even do it in a string. Okay, give yourself a string and try to find this. Okay, see if you're able to find it.
Unless your screen is stuck, I guess.
It's stuck. Okay. It's fine now?
Yeah.
Cool, thank you. So, okay, try to implement binary search over this, right? And see if you're able to find this index, right? Then try to understand how monotonic functions work, right? Or what are monotonic functions and how you can actually convert every question in a monotonic function. So, take this problem. So, this problem is 1613C. Okay, 1613C, right, in code forces, right, and try to form the monotonic function. Search, try to form monotonic function and binary search the answer. Actually, even before this, do you guys know what upper bound and lower bound is exactly? Like lower bound I told you right now. So let's say you are trying to find in this array 1 2 2 2 2 3 4. If you are trying to find 2, there are a lot of 2's, right? So lower bound will return this index and upper bound returns this index. Okay, lower bound returns the first two, upper bound returns the last two. Okay, now it's just a matter of moving when the element is equal, right? So if the element was equal in lower bound, it thought that R should move here. Now L shouldn't move across it, but in upper bound L moves across when the element is equal. That's the only difference. Now I won't be telling you this, you implement it yourself. Implement upper bound and lower bound yourself and try to do it, right? So implement upper bound and lower bound. Just tell me one more thing. Just everyone type in the chat. How many of you have had a little problem in today's class in understanding binary search? Just write a +1.
It's not something that I won't get, but I need to think of it. Might be getting that intuition.
Okay, okay. So even if you don't like completely understand what I told right now, just write a +1. It's fine. I am planning to maybe take a harder binary search later then, because I didn't
Okay.
discuss like lot of problems right now. They might be pretty hard for you if you are just starting out with binary search.
Something
I
on
think
Dhawal's
the
line that he
difficult
said,
part,
we can
what I found in
move
today's
the
class was that
Nimish's concept
it's
of
not the concept, it's just that
lessons for
the
life in
f
the
of
morning
x, the function
and
that we need to come
put
up with,
Yes.
the news
I think that
late
will be the
and
difficult
as
part.
Dhawal
That's all.
tell to connect
Okay.
the
Baki,
talking point to
understanding
news,
why
it would
binary
make a
search
good
works
loop
and how to
there.
implement was
But
clear.
yeah,
Okay, okay. So basically, you're not able to form the monotonic function, and you're not able to prove why it is monotonic right now. Something
Uh,
close to that.
Not proving, but like the actual implementation or logic behind getting it
was it the context
like
the
okay for the
compilation ones that you said
last question that we discussed, that
weekly
was quite
ones, then
clear
it
for
goes
the
the
poison question.
summing up
But for
reward.
let's say the task scheduler, I think I'll have to like think of something else because we have a bound over there, right? It is n, we can't go over n. So yeah.
Okay, okay. So basically, there's one more thing in binary search, like whatever I talked about. So like let's take the exact example of task scheduler, right? So in that problem, so every problem that you can binary search over the answer, you are basically changing what the question is asking. So instead of you solving the problem with what is the minimum value, you just solve the problem with is the value possible, and just binary search over it. Right, that is one major thing that I wanted you to understand. I'll just read the comments, give me 2 seconds. Right, so understand how find minimum value or minimum or maximum value changes to is value possible or is value x possible. Right, maybe I'll find more binary search questions, minimization maximization problems. Right, and I put it up the easy ones. I think I took very hard examples right now. The poison dagger was a better problem, but again, I'll find more easy problems and I'll try to put it in the sheet, but I'll put 2 3 harder problems as well so that we can discuss it later. Right, so again I'm planning to take this binary search class over again maybe in this week sometime, because there are few concepts that I didn't discuss with you at all. Right, I'll ask you, or maybe a bit later, how whatever is convenient for you guys. Right, but right now, please do this. Please at least do 0 and 1. Please implement upper bound, lower bound. Please go implement binary search yourself. Okay, maybe start with a very basic binary search, find an element in the array and the array, or report it's not there. Right, do that also. Okay, if it's not there, L always jumps over R, or R jumps over L, and you'll know that okay, this it's not there. Right, then implement binary search over this binary string or 0 1 array, and find the first place where they split. Right, do this, do at least try to do this. Then if you're able to do this as well, it's really nice. Otherwise, please keep asking queries and doubts. Okay, binary search is a hard thing, and it's actually very much required later. Right, knowing binary search, like, this thing is used at such harder algorithms. Like, every place you can binary search it. Right, almost every problem can be minimization measurement problem, everything can be converted into binary search problem. There are even problems in graphs. Right, there was a problem that I solved in graph. It was like, what is the minimum weight of the edge that should be to connect the graphs, let's say. Then instead of the question asking what is the minimum edge, I just binary searched over, is this edge weight possible to connect all the components. Then you realize that I just had to write that one monotonic function, and the whole binary search thing remained exactly same where it was. I didn't touch it. The whole idea of binary search just changed the question completely. Right, while introducing just a log and factor. Right, okay, I'll give more easier problems, okay, to understand it, to try it over. But please try these at least. Right, write a binary search function that works for you, and always use that. Okay, once you write this function, right, you just use that exactly same function. Just what you have to do is, where you are comparing where is 0 and 1, you just put this f of d, right, or f of x, however I put it here. Right, so maybe I'll replace few questions, and let's see. Okay, let's see when we can have another class. Right, okay, I read the comments. Work to get the intuition, really appreciate the thought, need to get method in practice. Yes, concept is clear, but I need more practice with the sums. Yes, binary search problems require a lot of practice. I mean, we're struggling getting intuition implementation of few sums. Okay, I'll try to put easier binary search right now, and I'll reserve the harder ones for later then. Cool. Again, if you have doubts, you stay back if you want to ask something. Again, please make use of queries. Please ask lot of queries, lot of doubts. Right, like, it will just help you. And in binary search, I think you need to ask a lot of doubts. Right. Okay, maybe I'll find more binary search problems and I'll put it there. In some problems, you can just open it and think how to make it monotonic, how to search over it. And maybe just solve like 3 or 4 problems, know how to binary search over the answer, then you'll be able to think about it, how to do it. And after solving few more problems, you'll be very clear. Right, so maybe search 2-3 problems, then go find problems, or I'll give you more problems, and just try to think how to build a monotonic function here, how to build a monotonic function here. Right, and again, like, a bit more harder thing is to understand how the function isn't monotonic. Sometimes the functions are parabolic. There you cannot binary search. There, actually, even in parabolic function, you can binary search on the slopes. Okay, that we'll see later actually. Okay, that is some advanced binary search that I'll talk about later. Right now, please do whatever I said right now, and I'll give you a few easier problems. Right, cool, you can leave them. Thank you.